Hey there, and welcome to this next lesson on high level mathematics. So, we're continuing to look at algebra. This time, we're looking at types of equations. So, we've looked at equations before in the general sense, what they are, how do we like manipulate them to then find unknown values and things like that. Now, we're looking at various types of equations. So, that will apply a lot of what we've already learned. Um, but they're these different types. We're going to see when we would use them and what purposes they essentially serve. So here we've got our lesson plan. So we're looking first at identities, which is something that we typically use to rearrange things. And the identity then captures that information that we can then use and remember. Formulae, which is something that shows relationships between different variables. We've already seen some of them. Proportionality, we've looked at proportionality as well. Now we're going to see how do we essentially extract an equation from a proportional equation. And then we're looking at functions. So that's a big topic. You see we've got three sections there. We're looking at functions, just what they are and how do we use them. What are composite functions, basically when we put one function inside another. And then we're looking at inverse functions. So if we have a function that does a particular thing, what is then the inverse that does, the opposite thing? How do we work that out? So that's our plan for today. So let's look at identities. Quite a few things we're working at today, but they're relatively small topics. So identities is the small things we're just looking at quick. Um, so an identity is an equation that's basically always true, regardless of what the values are. It's basically showing a way of rearranging something. And if we actually tried to solve an identity, it would be kind of pointless. It would come to zero equals zero, because it doesn't actually carry any information in terms of like the variables in it. We just use them to help simplify or to change a different equation into some other form. So one example would be something like this. This would be an example of an identity that's good to be familiar with because this is the kind of result we can get. Say if we have x squared minus b squared, it can be factorized in this way, and vice versa. If we have something factorized this way, if we expand it out, you see the AB term cancels out, and we're just left with a squared and b squared. Some where you might come across something like this is like say if you had a quadratic equation of x squared minus 64, and you see there's no x term, it's just x squared minus 64. If you was to factorize that, you could use this identity. It's essentially going to be x plus 8 times by x minus 8 because um, 8 squared is basically 64, isn't it? So that's one example where you might use this identity. And it's good to be familiar with this one. This is one that examiners love to use, because it can catch people out. You've got things like this, which, essentially are like identities expressing our distributive laws. So, where like you got B plus C. If you multiply that n by A, A is essentially multiplying the B and the C individually. Similarly, if you've got x times a and you take that to the power n, it's like the same thing as taking each one to the power n individually. So you see how everything, each operation distributes over one less on the whole bid mass hierarchy, but not two less. That's why if you had x plus y to the power n, that wouldn't be the same thing as x to the power n plus y to the power n. Oh, excuse me. So that's one thing to be mindful of. You got another identity like this one. So you might be aware of this one, you might not be. This is something from trigonometry where we have our trigonometric functions here, sine, cos, and tan, and they're related in this way. And so this is another identity, again, which comes from just the definitions of what sine, cos, and tan are. If you tried to solve this equation, again, it would just come to zero equals zero. This just shows us a relationship between the three and how we could perhaps rewrite tan in terms of sine and cos or vice versa. So that's identities, really. Not much there. Just important to be aware of what that word is. An identity equation is something like that, where it's just showing something how it can be rearranged or put in a different form. Formulae is something entire like something different, and it's where we're showing a relationship between two or more variables. So it expresses that relationship between those different variables. It's not just a rearrangement of terms like an identity. It actually provides a rule to essentially calculate one quantity when other related quantities are known. um, and we use them in various applied subjects, not just math, physics, engineering, economics, finance, so on and so forth. That everywhere you're going to have different formulas for different things that we can apply. So here's one example, which we've already seen, which is the quadratic formula. So we've seen how this shows a relationship when we have a quadratic equation. This formula here shows the relationship between the solution x with the coefficients of that equation a, b, and c. And with this formula, if we know what those coefficients a, b, and c are, we can then calculate the solution, and that's the formula. Another formula would be something like this, like density equals mass over volume. A formula for calculating density if we know what the mass and volume are. Likewise, if we knew what the density and volume were, we could calculate the mass, because that would be density times volume. This is something we'll look at in a sec when we're rearranging a formula. We've got formulas like this that you might or might not be familiar with. A squared plus b squared equals c squared. This is something known as Pythagoras' theorem from trigonometry, which relates three sides of a triangle, a right angle triangle. So that's one formula that we can then use. If we know two sides, we can always find the third. And then a equals pi r squared. That's the area of a circle. It shows, how the area of the circle is related to its radius, and vice versa. So that's the important thing. If we can calculate the area of the circle if we know its radius. Similarly, we could calculate the radius of a circle if we knew its area. And so that's the importance of formulae and these relationships. And if you have enough of these relationships, you can be very versatile in how you solve mathematical problems. So let's look at changing the subject. So when we have a formula, say something like this. So this is for calculating the hypotenuse of a right angle triangle. You might not know what that means yet. Doesn't matter. You'll learn about this when we move on to trigonometry in quite a few lessons time. We could rearrange this if we wanted to. So say if we wanted to make B the subject. So at the moment, like this, C is the subject. And what that means is we've got C equals some expression of other variables. And that's what it means is C is the subject. C is the focus here. And if we want to now rearrange this to make B the focus, so B the subject. So it's B equals something. How we do that is we essentially just use the same skills as if we were trying to solve for B. So say here we could square both sides to cancel out that square root, because we want to try and get the B squared out, but we can't if it's inside the square root like that. Then we could subtract A squared from both sides to get B squared by itself, so we've got C squared minus A squared on the other side. And if we square root, we'll get C squared minus A, the square root of C squared minus A squared is our value for B. And so you see there, it's essentially the same skills as if we were trying to solve for B, but you're not going to get some numerical answer. What we're going to get is a formula. You're going to get A in terms of, we're going to get, B in terms of A and C. And likewise, you might want to try this yourself. If you try and make A the subject, you'll then get A in terms of B and C. And it will look very familiar to what we've just done there. We could take another example of an equation like this. Probably haven't seen this before. This is an equation from a subject known as kinematics. You'd look at this if you was doing like A-level physics one day. But say here if we just think of this like a general equation with many variables here, we've got D, V, T, and A. We want to make A the subject. What would we do here? Okay, we want to just gradually get that A by itself. So let's subtract away the VT, and I've basically swapped the equation around, so I'll get the A on the left-hand side. Now, I could multiply both sides by 2 to get rid of the half. And now, if I divide both sides by t squared, because, we've got the t squared is multiplying the A, so if we divide, we'll get rid of it. And there we go. Now we've made A the subject. So now we can know what A looks like in terms of D, V, and T. And again, you might want to play around with this yourself and see, could you make V the subject? Or perhaps could you even make T the subject? That would be a little bit trickier. We're going to look at a simpler example of how that would work here. So this isn't an equation from physics or trigonometry or anything like that. This is just a made-up equation. And say if here we wanted to make y the subject, which, okay, we've now got two occurrences of the y here. Like, how would we deal with that? Well, first of all, get the y's together on one side. So we've got the yx term and the y term. So what I've done is I've subtracted y from both sides and I've added 3 to both sides. and that will get this. We want to get the y, just one occurrence of the y. So, okay, we've got two occurrences. How, and we can't just add them together necessarily. How do we bring them together? Well, we've seen this before. It's through factorization. So you see, we've got multiple terms here with a common factor of y. We can take out that common factor. So we've got, y times by x minus 1. And so now you see we had two occurrences of the y, and now there's only one. And we can now solve this by simply dividing by x minus 1 to get rid of that x minus 1 that's multiplying the y. And here you go. And you get like this little algebraic fraction, x plus 3 over x minus 1 is our solution. So that's an example of changing the subject, which is quite an important thing to be able to do. But notice that it's using the exact same skills as solving an equation, but you're just not going to get a numerical answer. You're getting to get something, some expression in terms of the other variables. And yeah, you need to be confident in doing that. So let's move on to proportionality. So we've seen a bit of proportionality before. Now we're going to look at it in algebraic form. So if we had, say, two variables like this, like y is proportional to x, we have this little symbol here which denotes proportionality. So, and it reads left to right. So we've got y is proportional to x. What that means is that y and x essentially are going up and down. So we have this proportionality, y proportional to x. What does that mean in terms of an actual equation? So we can put it as an equation like this. So this would be the most basic case, is if we had just y simply equal to x. But in general, it won't be like that. They're separated by some constant of proportionality, which is k, some just unknown constant. So it shows that, like, y is equal to x, but so essentially like a linear relationship, um, which can be plotted as a straight line on a graph. And then it's like the k is just then determining how strong that relationship is. Is it very steep, or is it then very shallow? Or it could be negative, for example. So um, that's kind of the thinking behind it. So that's the main thing you need to know, is that when you have one variable proportional to another like this, it means that they're basically equal to one another with some constant of proportionality that, this k that separates them. And so then, in order to find out what that k is, we need a boundary condition. So you see, depending on what that value of k is, it's kind of determining how steep that relationship is at, the gradient, if you're familiar with that term, uh, is going to be. And in order to fix it to a particular value, we need to know a particular constraint, which is basically, we need to know a value of y and its corresponding x. Because, okay, x and y are variables. X is varying, and then based on the that variable value of x, y has a variable value as well. But we just need to know one particular point for a particular value of x. What is the corresponding value of y? And we've got one here. If y is 6 when x is equal to 2, then we can easily just substitute that in, and we get a little expression for k, a little equation for k that we can then solve, and we get k equals 3. So that is kind of a simple case. And it's really all we need to know, is that when you have that proportionality, we can convert it to essentially a fraction like this, but we then need some kind of boundary condition to find out what that unknown constant is going to be. So if we put that k back into our original equation, here you go. This is the equation that relates the x and the y. If we have an inverse proportionality, remember, it's just essentially the reciprocal. So we have y is proportional to the reciprocal of x. That's what inverse proportionality is. And if we wanted to work out what the equation is, we'd do that in very much the same way. So, okay, y is basically equal to 1 over x multiplied by some constant of proportionality, k. If we have a boundary condition like this, we can always substitute that in to get 5 equals k over 4. And if we times both sides by 4, we can then solve what the k is. And so we put that back into our original equation, y is equal to 20 over x. So that's how we do something like that. We can take a proportionality between two variables and essentially convert it to an equation. So we can take more complex proportionalities like this, say p is proportional to q squared, works in very much the same way. So, okay, p is equal to k times q squared. And if p is equal to 36 when q is equal to 3, that's our boundary condition. We can then substitute in, you get something like this, and we can then solve to get k equals 4. And so therefore p is equal to 4q squared. So you could think of this like, say, like what we've seen before, like you might have, say, distance. No, sorry, area. The area of some shape is equal to the distance squared. And then, okay, so the area of some shape is going to be proportional, sorry, to the distance squared. We've already seen that before. Now, depending on the precise shape we have, we don't know what the area would be uh, for that distance. It depends on what the distance is. Like we have different formulas for different shapes, don't we? And so, but we know it would be of that kind of form. And like say that equation we saw of a equals like the area of a circle equals to pi r squared. The area of the circle is proportional to r squared. So therefore, the area is equal to some constant times by r squared. And when we find out what is that constant of proportionality, it turns out to be this unique value pi. So that's like an example of doing this like in real life, like a real life example. And generally, you just need to be aware of how we actually work this out for these simple examples when you're given the information that you need. One last example is say, okay, if we had m is inversely proportional to the square root of n. Okay, inversely proportional means 1 over n, and we're talking like not n, but the square root of n, so it's 1 over root n. So that means m equals k over root n. We have a boundary condition like this. We can substitute it in. So square root of n is 7, or technically plus or minus 7. So if we then solve this, we'd technically get k equals plus or minus 21. You may not need to be that specific. Depends on the question. And if we substitute that back in, we basically get m equals 21 over, that should be root n, not just n there. So 21 over root n. So let's take a more sort of complicated example, like this kind of example you might get in an exam where we've then got to apply that. So say if we had something like this. So if we've got a is proportional to b squared, but a is also proportional to the square root of c, and we're given these boundary conditions, if b equals 4.5, c equals 2.25, what's the value of b when c equals 8? So we need some kind of equation for b in terms of c to then find out, what b is going to be when c is equal to 8. So taking that information, those proportionalities we were given, a is proportional to b squared, so therefore a is going to equal to some constant times b squared. A is also proportional to the root of c, so a is going to equal to some constant times root of c. But the key thing here is that they're going to be two different constants. You can't just use the same one because it's two different proportionalities, two different relationships. So, okay, we want to get b in terms of c. So, okay, we can essentially use like the techniques we've seen with simultaneous equations. Because we've got a in terms of b, we've got a in terms of c. Well, if we substitute one into the other, we've then got b in terms of c. Like these are both expressions are equal to a, so we can set them equal to one another because they're both equal to a. So now we could try and rearrange this to make b the subject, like what we did earlier. We get something like this. The key step to do here is because, okay, so we can see we've got b squared is like proportional to the root c, and we've got this constant which is j over k. Like j and k are both just unknown constants, so j over k is just an unknown constant. So what we could do is just replace that by some other constant, l. It doesn't matter because they're just unknown constants. So then now, given that boundary condition we had, b equals 4.5, c equals 2.25, we can substitute that in and work it out. Like here I've decided to convert them into fractions, and I can work them out like this. And then if I do a bit of a fraction arithmetic there, I can work out what the L is. You can do it whatever way you'd prefer. And so once we've got that, we know that the B, I can substitute that back in. So now we've got our equation in terms of B and C, no unknown constants. Now we can just simply use this to find out the final answer that they've asked us for. So you go back to the question, you see what it actually was asking for was what is the value of B when C is 8? Well, if I just substitute in C equals 8, I can now work out what that is. So root 8 is basically going to be the same thing as 2 root 2 using our understanding of surds. So we get 27 root 2. Now B is the square root of that. So it's like we're getting a square root inside a square root there. Something like that you'd have to put into your calculator. And to 2 decimal places, I get it as 6.18. So that's a proportionality question. So you see, there's some simple examples you might get asked there, but then this is a thing that they love to ask, certainly on higher papers, where you've basically got three variables and you've got a proportionality between, say, A and B and C, or something like that, and then you have to know how to combine them together to then get a new relationship between, say, A and C or whatever. Um, so make sure, yeah, you're comfortable in doing that. The key step there being doing a substitution, and then when you bring your two unknown constants together, if you just got one, like what we had here, one divided by another, you can just replace it with a new constant and then use your boundary conditions as usual. So that's the kind of the tricky step, and then from there, it's kind of the same as what we've seen before. So let's move on to functions, because it's a big topic, and so there's a few things we need to unpack. So function, first of all, what is a function? You can see a function simply just like a machine. It's like it takes an input and then it spits out an output. So that input is what's known as an argument. It's a funny word for it, but it's basically you see it like a machine. You put an input in one end and output comes out the other end. Now each possible input to the function has exactly one output, although multiple inputs can produce the same output. And functions, they basically provide a compact notation. So if we've got a whole series of operations going on, and maybe it's a series of operations we're going to use many times over, and so we don't want to keep writing it all out, we can put it into a function like which typically would label like f or something. And so that function f represents all those operations. So it gives us that compact notation uh, for doing things. So yeah, that second point is really important. That's a key property of a function, is that it can only produce one output. You can't be producing multiple outputs, but it's fine the other way around. So here we go. This would be an example of a function. And if we break that down, it's basically like this. Like you're taking x and you put it into this blue box, and f. What is that f doing to it? You remember going all the way back to when we first started algebra and breaking down what is actually happening in that expression there. What you've got the x, you're multiplying it by 2, and then you're adding 1, and that produces the output that we then label f of x, or sometimes you might label it y. So here's an example of another function, because you see it fits the criteria we had, whereas this would not be a function in and of itself, because remember, like we said, it can only produce one output. You can't have an input producing multiple outputs. And we've seen before that a square root produces two answers, doesn't it? Like the square root of 4, for example, would be plus or minus 2. And so that's not allowed in a function. You can't have two possible outputs. So if we could have something like this, like a quadratic, which would be an example of a function. A quadratic function is perfectly fine. If we wanted to know what is the value of that function for a particular input 3, we put in a value of 3 and it just replaces where the x goes. We can then use our rules of Bidmas to calculate that out to be 9. If we did it the other way around, like something like this, f of x equals 0, and we had to solve that, what that's basically saying is what input value x will produce an output of 0. So in other words, it's basically asking, when does that quadratic equal 0? Which we know how to do. Like we could, solve that through factorization quite simply. So that's what a function is. Give you input, it does a bunch of operations, produces an output. We need to know, if given an input, can we calculate an output? If given an output, can we calculate an input? What the input is that would produce that output. And we know, when is something a function, when is it not a function? So here, now let's look at composite functions. So this is when you're essentially kind of piecing them together, when you might have a function goes into a function, into another function, something like that. So say here, we've got two different functions. So typically F, G, H are the letters that we use to denote functions. And so here's our notation, f of x. That means we've got a function f that does a series of operations and it takes its input x. And likewise with g. So this would be then our function that we saw before. Now, if we want to do the composite function where we basically do f and then do g, it's like you're taking that f of x and then you put that into the second function g, which does an exponent of 2 and then it subtracts 4. So you see what g of x does there. It takes an input, it squares it, and then it subtracts 4. And so that would then be this here, g f of x. So you see there where there's a function g, which was g of x before, x was the input. Now it's like we're placing that x with the f of x. Now, you see this, it's kind of cumbersome notation with a lot of brackets. So for neatness, we tend to put it like this, where we just have gfx. And what that means is the composition of f first and then g. And that's really, really important. Like just like with order of operations in general, order matters. And so the order of a function is going to matter. And we can take a look at that here. If we do gf of x, so you're taking the f of x, 2x plus 1, and we're now putting that into g as input. So input g of x normally takes just x. So where there was an x before, we put a 2x plus 1. So it's 2x plus 1 squared minus 4. So this would be what that function looks like, that composite function, which we can just expand out, and you see it gets a quadratic like this. Now notice if we did the opposite, where we take the g of x first, which is x squared minus 4, and now we put that as input into f. So where there's an x in f, we now put x squared minus 4. So you see we get two lots of x squared minus 4 plus 1, and we can expand that out to get this quadratic. So you see two completely different answers depending on what order you put them in. So that's really, really important. And so you see you're kind of reading outwards from the input. So g f of x, you're basically applying f first and then the g. You see how you're reading from right to left, not left to right. So it's a little bit, kind of counterintuitive in that way. But when you understand the notation, where like the f is actually going into the g, and you had the brackets, but we're just kind of losing the brackets, you can see why that is the case. Finally, you could also compose a function with itself. So here we could do f of x. What would that look like? Well, we have a compact notation for that. It'd be f2 of x. And we do normally phrase it like that, like f2 of x, not f squared, because f squared is something different. Like squaring something means like we're doing 2x plus 1 times 2x plus 1 in like double brackets. That's not what we're doing here. We're doing a composition where we've got 2x plus 1 and then we pass that as input to f again. So that would look something like this. So you see how we have 2x plus 1? And then with 2x plus 1, we put a 2x plus 1 where the x is. And so it might be a little bit confusing when you're composing something with itself like that, but hopefully that makes sense. And then you could always expand that out and simplify, and you see we get this expression here. So that's composite functions, where you're passing, where one function's output becomes input to the next function. And you could imagine doing that multiple times. You'll never get asked anything involving more than 3 functions, though. Typically, it's only 2, but you might get one asking 3. But it's the same logic. You can just then apply, okay, the output of G would then go into H, for example. Now we're looking at inverse functions. So inverse function is basically you have f does a particular thing. Well, f inverse does the opposite. So say if you have something like this. So we're doing h of x is equal to 5x minus 6. Now we want h inverse of x would do the opposite, and that would be expressed by this equation here. Now notice again we have this kind of like power, like -1. Now we've seen that before with like a variable or a number. It's a reciprocal. It means do 1 over that thing. Here it doesn't. This is a function, and the notation means something different. Here -1 means inverse. So it's not doing reciprocal. It's not like I'll just do 1 over 5x minus 6. It means do the opposite step. So here, 5x minus 6, you see what we're doing is we've got x, we're multiplying by 5, and then we subtract 6. So you see h inverse, what it does is it takes x, it adds 6, and then divides by 5. So you see it's doing the opposite, the reverse steps in the reverse order. So with a simple one like that, we can kind of work it out kind of almost intuitively. So you see x, it's basically multiplying by 5 minus 6. H inverse would then add 6 and then divide by 5. And you see it kind of would undo the work. Like if we did x into h of x and then take that output to h of x and pass it into h inverse of x, it would take it just back to x, what we started off with, the input. And we can see that here. If I do h inverse of x, like composition, you can see it simplifies down to x. Similarly, if I do it the other way around, it doesn't matter what order I do it in because they're both basically opposites of one another. They just cancel out and you produce x. And x, so x is like the identity of of functions. You know, kind of like in the same way, like if you divide a number by itself, it becomes one. You know, it kind of cancels out, and times it by one doesn't do anything. It's kind of like the same thing here, where if we do the inverse of a function, it produces the identity function x, which is basically the function where you give me an input x and I give you an output x. It just does nothing. So that's the reason why it comes out to x and not 1 or 0 or something like that. X is the function that basically is doing nothing. So finally, let's look at an example of calculating the inverse of something maybe a bit more complicated. So you might be able to see it by just looking at the steps that are occurring here. 7x minus 3 divided by 4, and then do the reverse steps of that. But how would we do this in a more rigorous way, say if it was something a bit more complicated? What we do is, okay, we let the output be y, for example, first. And then what we do is we swap the variables around. So where there was a y before, I put an x. And where I put an x before, there's a y. And I've put y star for, you will see in a reason why that is. See in a minute what the reason for that is. And you see now this equation is going to represent the inverse. Like x is going to be the input and y star will be the output of that inverse because I've swapped them around. Like you think about in that diagram where we have x, we apply a function and we get output y. If I literally swap those two around, like I flip the whole thing upside down, that's essentially the inverse function, isn't it? It's now doing the opposite things that would, you know, take you from what was previously the y and bring you back to the x. So that's what's essentially happening there when we swap the variables around. We're now flipping the whole thing upside down, and it's now doing the reverse process. So we know this represents the inverse function. We just need to make y the subject now. So what we do is we rearrange this in the same way we've done before. We can get y inverse, y star equals this. And the reason why I put a star there is because remember y before was representing the output of g of x. But the second that we swap the x and the y around, the y like x is always just the input. But y is no longer the output of g of x. It's now the output of g inverse of x. So that's why I put a little star there. You could do that. You don't have to, but you just need to be aware that the second you swap the x and the y around, the y doesn't represent the output of the function anymore. It represents the output of the inverse function. So just be mindful of that. We could take another example here with h of x. Again, I could make the output be y just for simplicity, you know, because you don't want to just have a h of x moving around. We could swap the variables around, and then now I'm going to try and rearrange this to make the y star the subject. And see, I've kind of skipped a couple of steps there, but I'm sure you'd be able to work that out. If not, you might want to pause here and just you know, confirm that to yourself. And likewise, that y star is now h inverse of x, not h of x. And so this is now the inverse function. You try composing them, these functions like with their inverse, you'll see it will cancel out to x. So that is how we would calculate an inverse function in a more rigorous way, which is certainly good when we're trying to do more complicated ones. Like now, trying to do the inverse of a quadratic, which is not something you'll likely encounter, although it's something you could quite easily work out. So just to make sure we've got all bases covered, I thought I'd show you an example here quickly. So suppose we have a quadratic equation, quadratic function here, and we wanted to work out the inverse. Here I'll just show you the different steps, explaining each step. So it's essentially completing the square first, because the problem is with the quadratic here is that we've got multiple occurrences of the x. We've got the x squared and we've got the x term. But completing the square gets us just one occurrence of the x, doesn't it? With the x plus 5 squared minus 30 there that you can see. And then we can just kind of swap the variables around like we have done before, and then rearrange to make y star the subject, and we get, you know, that's basically f inverse. So you can always pause on this slide and take a closer look at that. The problem is with this one is we then have to restrict the possible solutions we can have. Like x, we can only allow x greater than minus 30 because look at that inverse function. If x was less than minus 30, then we would get a square root of a negative number, and we can't have that. Like that's not possible. Likewise, like we saw before, the square root produces multiple answers. So it could be positive or negative. And so you see the values of we're kind of get two possible answers, greater than -5 or less than -5. So what we do, I've put there where f inverse of x is greater than -5. So we're restricting ourselves to only the positive answers to that square root. So things like this, the, you know, it's the square root wouldn't normally be a function, but we can make it into a function if we kind of restrict what we accept as inputs and outputs. Um, so that's something that can be done. So quite a sort of more advanced problem this here. And it's yeah, I don't want to spend too much time on it because I think it's unlikely you'd get asked something like this. But you see, using completing the square, you could do the inverse of a quadratic. So yeah, I would encourage you to take a quick look at this and see how that works. But that's it for today. So we looked at those different types of equations, identities, formulae, functions, and how they all work. Wanted to add here that functions play a pivotal role in computer programming. So any of you that might be interested in going into computer programming, coding, and things like that, functions. So when we might have a whole bunch of code or mathematics that does a particular thing, we can put it into a nice function and then repeat that over and over again. That's what functions are really good for. Um, and yeah, so we can take a complex problem, break them up into various little functions that we can easily then just call and reuse as and when we need to. They're very predictable, because you give it particular inputs, it will always produce the same outputs because it's its own confined thing. Like say if we have f of x, and that was part of a bigger calculation, it's its own contained thing, isn't it? Like the contents of that function is contained within that f of x. So that what makes it really handy. Like what we've seen is like with compositions uh, and recursions or iterations. That's basically like when you're doing a function over and over again. We can do that very easily if we've got a function, and computers excel at that kind of thing. Doing that simple task over and over and over again. So yeah, functions are a very pivotal they play a pivotal role in computer programming if you're interested in that sort of thing. So here we go. Here's our takeaways for today's lesson. So coming up next, we're going to be looking at plots. So we haven't really looked at how we would graph an equation, which it allows us to essentially visualize all solutions of an equation at once and see the general shape it takes. So very powerful thing, graphs. So we're going to be looking at that next time. So I'll see you there.